So, I mean, think about your body like a bustling, highly organized city, you know?
Right. Yeah, a really complex city.
Exactly. You've got power plants generating energy, waste disposal systems clearing the streets, complex communication networks sending signals from downtown to the suburbs,
Mhm.
and billions of tiny workers just keeping the whole thing running smoothly.
Yeah, the cells.
Right. And when we normally think about a threat to the city, like a threat to you, physically we picture a tangible attack.
Something you can actually see or feel.
Exactly. We picture a physical impact, like an earthquake leveling buildings or an invading army of bacteria just storming the gates. There's a visible, undeniable mechanism of injury.
It makes intuitive sense to us, you know? A physical trauma occurs, structural damage happens, and then the body's emergency systems respond.
Yeah.
You can see the bruise, you can feel the fever, you can measure the physical disruption almost instantly.
But then you encounter ionizing radiation.
Right, and that changes everything.
It really does. Suddenly, that entire framework of a visible, tangible threat completely falls apart. I mean, radiation doesn't drop a bomb on your biological city.
No, it doesn't.
It doesn't send in an invading army. It is entirely invisible. You can't feel it hitting you. It doesn't trigger a sneeze. It doesn't leave an immediate mark.
Yeah, it's insidious.
It acts like a microscopic saboteur, a saboteur that infiltrates the city completely undetected, walks up to the buildings, and just starts silently removing the mortar from between the bricks.
Which is a terrifying concept when you really stop to think about the scale of it.
Oh, absolutely.
Because depending on where that saboteur strikes, the city might just patch the brickwork tomorrow and keep standing as if nothing happened.
Right, like no big deal.
But if they remove the microscopic mortar from a critical load-bearing pillar in the city's main water supply, or the central power grid,
Oh, wow, yeah.
the whole system could collapse days or weeks later, seemingly out of nowhere.
And that's what we're looking at today. Welcome to today's deep dive. Today, we are hunting down that saboteur.
We really are.
We are tearing away the dense medical jargon of radiobiology to understand exactly what happens to the human body when it encounters ionizing radiation.
And we're basing this on a really fantastic breakdown. Right?
Yes. A highly detailed presentation and review of Bouchong's Human Biology by Kelly McCowan. So we're not talking about science fiction movies with, like, glowing green rocks.
No glowing rocks here.
We're looking down to the exact atoms that make up your cells. You want to find out how this invisible force dismantles the mortar, why some parts of your body are incredibly vulnerable, while others are surprisingly bulletproof.
Yeah, the bulletproof ones are fascinating.
And what the biological reality is when the entire city experiences a massive, overwhelming attack.
To really grasp the mechanics of this, we have to fundamentally shift our perspective.
How so?
Well, we have to zoom all the way past the macro level, past the organs and tissues, past the blood vessels and the bones.
Okay, down to the micro level.
Exactly. Down to the micro level of electrons and chemical bonds. Because before we can understand how the city collapses, we have to look at the exact chemical makeup of the target itself. We have to look at the elemental composition of you.
The composition of you. I love that. So let's break down that recipe. What is a human being actually made of at the molecular level?
The numbers are pretty surprising.
When you look at the raw data from McCowan's review, the percentages are almost hard to believe. If we strip away all the personality and the memories and just look at the raw materials,
Okay.
You are basically walking, talking water.
Literally.
A full 80% of the human body is just water, hydrogen and oxygen atoms.
The universal solvent. I mean, it provides the medium for all the chemical reactions that keep you alive.
Right. So that's 80%. Then 15% of you is protein.
Yeah, the structural building blocks. Muscle fibers, the enzymes doing the heavy lifting.
Got it. Then 2% are lipids, which is basically the fat that stores energy and insulates the body. 1% is carbohydrates, your primary fuel source. And another 1% is just a mix of miscellaneous trace elements and minerals.
Right. But there's one piece left.
Yeah, the final 1%. Just 1% of your entire physical composition is a molecule called nucleic acid, which most of us know by its much more famous acronym, DNA.
The master blueprint.
Yeah.
And when you lay out those percentages side by side, a profound biological irony emerges.
It's the irony.
Well, radiation is completely indiscriminate. When a wave of ionizing radiation passes through your body, it doesn't aim.
It's just a wave.
Exactly. It can interact with absolutely anything in its path. It can hit the water, the proteins, the lipids.
Okay.
But even though you are overwhelmingly made of water, and statistically, A radiation photon is almost guaranteed to hit a water molecule.
Right, because it's 80% of the target.
Exactly. But that tiny, seemingly insignificant 1% of DNA is the ultimate critical vulnerability. It is what radiobiologists call the radiation-sensitive target molecule.
Because hitting the water just doesn't matter in the grand scheme of things.
Think about the role of water in the city analogy. It's the fluid in the pipes.
Okay.
If a saboteur disrupts a single drop of water, the city doesn't care. The body has an effectively infinite supply of water, and water molecules are incredibly simple.
Just 2 hydrogens and an oxygen.
Right. If radiation splits them apart, they often just recombine a fraction of a second later.
Right.
Or the body flushes the disrupted molecules out and replaces them. There is no lasting systemic damage.
But DNA is different.
Very different. DNA is not a simple replaceable fluid. DNA is the central architectural blueprint for the entire city.
Right, it has all the instructions.
Exactly. It contains the exact instructions for how every single cell should function, when it should grow, what proteins it should manufacture, and when it should die.
So if it hits the blueprint.
If the radiation hits the blueprint and alters a critical line of instruction, the consequences can cascade through the entire system. The cell might start building mutated proteins, or it might lose the ability to perform its function entirely.
Wow. Okay, so we've identified the high-value target, the DNA. But how does this sabotage actually work?
The mechanics of it.
Yeah. What is physically happening when an X-ray enters the room, passes into your body, and hits that DNA?
It comes down to a process called ionization, and it happens purely at the atomic level.
Okay, picture this for me.
Picture an atom as a tiny solar system. You have the heavy nucleus in the center acting like the sun.
Right.
And you have these incredibly small, negatively charged electrons orbiting around it at high speeds, acting like the planets.
Classic science class model. I'm with you.
When a wave of ionizing radiation, like an X-ray photon, passes through your tissue, it isn't just a beam of light. It carries a very specific high amount of kinetic energy.
Right.
If that photon happens to collide with an atom in your body, it transfers that energy. It essentially slams into one of those orbiting electrons with so much force that the electron is violently knocked completely out of its orbit.
Whoa.
Yeah, it's sent flying off into the void of the cellular fluid.
So it's like playing a microscopic game of billiards.
Exactly like that.
The radiation photon is the cue ball. It smashes into the atomic rack, and an electron just gets sunk into the corner pocket.
That is exactly the physics of it. But to understand the biological damage, we have to ask, what was that electron actually doing before it was knocked away?
It wasn't just hanging out.
No. Electrons are not just passive planets spinning around. They are the chemical glue of the universe.
The glue.
Yeah, the way atoms bond together to form complex molecules like proteins or DNA strands is by sharing their outermost electrons. They hold hands, so to speak, by sharing these negative charges.
So if an atom loses an electron, it loses its grip on the atom next to it.
Yes, the chemical binding properties of that specific atom instantly change. It suddenly has an unbalanced electrical charge.
Which means it's unstable.
Highly unstable. It desperately wants to find a new electron to stabilize itself, or it can no longer maintain the bond it currently has.
And that's where the problem starts.
That triggers a very specific, rigid chain reaction of destruction.
Okay, walk me through the chain reaction.
Step 1 is the ionization event itself. The cue ball hits, the electron is gone.
Got it. Step 1, ionization.
Step 2 is the altered binding property. The atom's chemical nature shifts because it's missing that glue.
Okay.
Step 3, because the bond is altered, the entire molecule that the atom belongs to changes its physical shape. It becomes an abnormal molecule.
Like a Lego piece that suddenly has its top studs sheared off. It's still a piece of plastic, but it no longer fits into the tower the way it was designed to.
That's a perfect way to look at it. And in biology, shape is everything. The function of a molecule is entirely dependent on its three-dimensional structure.
So if it's misshapen, it's broken.
Right. If a protein changes shape, it stops working. If a section of DNA changes shape, the genetic code is corrupted.
Yikes.
This leads to step 4, the creation of a biochemical lesion.
A lesion on the DNA.
Yeah, the altered molecule causes a localized failure in the cell's machinery. Then step 5, that lesion leads to the impairment of the cell. The cell either begins to malfunction, or, if the damage is severe enough, it simply dies.
Just from that one missing electron.
Just from that one, and then the micro becomes the macro.
Yeah.
Step 6. If enough individual cells undergo this process and die, you experience visible, measurable tissue damage.
And step 7?
Step 7. If enough tissue is damaged, the entire organ fails.
That is just a staggering domino effect. I mean, one missing electron, a particle so small we can barely even comprehend its existence, eventually cascades up into a failing kidney or a collapsing immune system.
It's incredible physics, really.
But hold on, let me stop you right here. Because this chain reaction raises a massive red flag for me.
What's that?
If the mechanism of damage starts so incredibly small, literally just a single missing electron, and the cascade is that severe, how are any of us still alive?
It's a very fair question.
I mean, we don't live in lead-lined bunkers, right? We are constantly bombarded by background radiation.
Every single day.
Cosmic rays from the sun hit us. The Earth itself emits radiation from materials like radon in the soil, not to mention the medical procedures. We get dental x-rays to check for cavities. We get chest x-rays for a cough.
We fly on airplanes.
Yes. We fly on airplanes at 35,000 feet where the atmosphere is thinner and cosmic radiation is higher. So if all it takes is one photon hitting one atom to start a chain reaction of cellular death, why doesn't every single X-ray result in organ failure?
It sounds like it should, right?
Are we just walking around constantly accumulating this microscopic atomic damage until we inevitably just fall apart?
It is the most logical question to ask when you understand the physics of ionization. And thankfully, the biological reality offers a crucial countermeasure.
Oh, thank goodness.
The chain reaction from ionization to organ failure is not an unstoppable freight train.
Okay.
At nearly every single step of that domino effect, from the moment the molecule becomes abnormal to the formation of the biochemical lesion, the human body possesses incredibly sophisticated enzymatic repair mechanisms.
Meaning the city has a maintenance crew.
A highly dedicated, microscopic maintenance crew. Your cells are packed with specific enzymes whose entire singular purpose is to patrol the billions of rungs of your DNA.
Just looking for damage.
Constantly. They are constantly scanning the molecular structure, looking for physical irregularities. They're looking for those Lego pieces that have been damaged.
Wow.
When they find a strand of DNA where an electron was knocked away and a bond was broken, they immediately initiate a repair sequence.
How do they fix it?
They cut out the damaged section, they synthesize the missing chemical components, and they stitch the DNA strand back together, perfectly restoring the original blueprint. The body is astonishingly good at repairing radiation damage and recovering from sub-A low-dose exposure.
Okay, I can feel my heart rate coming down a bit.
Good.
So the saboteur knocks the mortar out, but the maintenance crew is walking right behind them, packing new mortar into the cracks before the building can even think about swaying.
Exactly.
That makes me feel significantly better about sitting in the dentist chair while they put that heavy lead blanket over my chest.
It is a miraculous biological defense system. However,
Yeah.
we cannot let that sense of safety lull us into complacency.
Right. There's always a catch.
Because this brings us to a foundational principle in all of radiobiology and medical imaging. It is a concept known as ALARA. A-L-A-R-A.
As low as reasonably achievable.
Correct. Because here is the hard mathematical truth about those microscopic maintenance crews. They are amazing, but they are not infallible.
They make mistakes.
They are not perfect. Sometimes an enzyme misses a broken bond. Sometimes a radiation photon causes a complex double-strand break in the DNA that is simply too catastrophic for the enzyme to stitch back together properly.
Like dropping a whole brick instead of just the mortar.
Exactly. And sometimes, which is perhaps the most dangerous scenario, the enzyme attempts the repair, but it makes a mistake.
Oh.
It puts the wrong molecular piece back into the puzzle. It stitches the DNA back together, but the code is now slightly permanently altered. A mutation has occurred.
And a mutated blueprint is sometimes worse than a destroyed blueprint because the cell keeps trying to build things based on faulty instructions.
Exactly.
Yeah.
Because of that inherent risk of repair failure, the entire medical and scientific community operates under a very strict conservative assumption. There is no such a thing as a completely safe dose of ionizing radiation.
Wow. No safe dose at all.
We must assume that even the absolute smallest dose, a single photon passing through the body, has a non-zero chance of causing an irreversible mutation. Therefore, caution is paramount.
So every time you get an X-ray...
Every single time radiation is used, whether it's a diagnostic X-ray or a nuclear power plant protocol, the exposure must be kept as low as reasonably achievable. You want to give the saboteur as few chances as possible to slip past the maintenance crew.
It's risk management. I mean, yes, my car has a seatbelt, airbags, and a crumple zone. Those are fantastic repair and survival mechanisms.
Right.
But just because I have airbags doesn't mean I should intentionally drive my car into a brick wall at 5 miles per hour just to see what happens.
Precisely. The goal is to avoid the crash entirely.
We only use the radiation when the benefit of the medical information we get from the X-ray drastically outweighs the tiny risk of a cell mutating.
That is the perfect way to contextualize it.
Yeah.
So, we understand the weapon, the ionizing photon. We understand the high-value target, the DNA blueprint. And we understand the philosophy of minimizing exposure.
ALARA.
Right. But to understand why radiation sickness happens, we have to look at the battlefield itself.
Okay, setting the scene.
We have to know exactly where this DNA lives inside the body and what it is doing when it is most vulnerable to attack. We have to step up from the subatomic physics of electrons and enter the realm of cellular biology.
All right, time for a crash course in the architecture of the human cell. I mean, a human body isn't just one solid mass, right? It is a colony of trillions of individual living units called cells.
Trillions of them.
And while they all have different specific jobs, the basic structure of a human cell is relatively uniform. It basically consists of two major components. First, you have the cytoplasm. Think of this as the city limits. It's the bulk of the cell, filled with a jelly-like substance where all the factories and power plants float around the mitochondria generating energy, the ribosomes building proteins.
It's the busy working floor of the cell.
Yeah. But deep in the center of the cytoplasm, you have the second major component, the nucleus.
The vault.
And the nucleus is the vault. It is a heavily fortified, membrane-bound sphere that exists for one primary reason, to protect the DNA.
The structural separation is absolutely crucial. The DNA doesn't just float around freely in the cellular jelly.
No, that would be way too dangerous.
Exactly. It is locked away in the nucleus because it is so incredibly valuable. The factories in the cytoplasm just receive temporary copied instructions from the vault.
Okay, makes sense.
Now, if we look at the trillions of cells making up the human body, we can categorize every single one of them into two distinct factions, based entirely on their ultimate biological purpose.
Two factions. What's the first one?
The first faction is the genetic cells, which are also known in biology as germ cells. These are the reproductive cells of the body.
Okay.
For males, it is the spermatogonium, the sperm cells. For females, it is the ogogonium, the egg cells. They have a singular, highly specialized mission. They do not exist to keep you alive. They exist solely to carry your genetic blueprint to the next generation.
They are the escape pods for the DNA.
Yes, escape pods. And the second faction comprises the somatic cells. And the definition of a somatic cell is wonderfully simple, literally everything else.
Everything else.
If it is not a sperm or an egg, it is a somatic cell. The cells making up the skin on your arm, the neurons firing in your brain, the muscle fibers in your heart, the lining of your stomach, the marrow in your bones.
Got it.
They are all somatic cells, and their job is to keep you, the current organism, functioning and alive.
Because these two factions have fundamentally different missions, one is focused on creating a new human, the other is focused on maintaining the current human they have to multiply in very different ways, right?
Yes, entirely different cellular life cycles.
And the moment a cell decides to multiply is the exact moment it becomes most vulnerable to our radioactive saboteur.
That's the crux of it all. Yep. Let's start with the genetic cells, the sperm and the eggs. They proliferate through a highly complex process called meiosis.
Meiosis?
The goal of meiosis is not simply to make a copy of the cell. The goal is to prepare for reproduction.
Yeah.
During meiosis, the genetic cell begins to divide. But it does something very specific. The cell itself divides twice, but the DNA vault, the chromosomes inside the nucleus, is only duplicated once.
Wait, which feels like a math error at first glance. Like
Yeah.
if you divide a pie twice but only bake one extra pie, you end up with smaller slices.
Exactly, and that is the intentional biological design. By dividing the cell twice, but the genetic material only once, the final resulting sperm or egg cell ends up with exactly 1/2 of the normal number of chromosomes. It is carrying a half deck of genetic cards, which makes perfect sense, because its entire destiny is to eventually meet up with another genetic cell from a partner, combine its half deck with their half deck, and create a brand new genetically unique human being with a complete, full set of chromosomes.
Okay, so meiosis is for making half-decks.
Right.
But my skin cells don't need to do that. I mean, if I scrape my knee falling on the sidewalk, my somatic skin cells don't need to combine with anyone else's skin cells to heal the wound.
No, definitely not.
They just need to quickly replace the exact skin that was lost.
Precisely. Which brings us to how somatic cells proliferate. They use a much more straightforward process called mitosis.
Mitosis. Okay, so meiosis for germ cells, mitosis for somatic cells.
Yes, in mitosis, there is no genetic shuffling, there are no half-decks. The goal is pure replication. One parent cell undergoes division to form two absolutely identical daughter cells, exact clones. The DNA blueprint is meticulously, perfectly duplicated, and you end up with an exact one-to-one clone of the original parent cell, ready to take its place in the tissue.
And this continuous loop of a cell growing, performing its job, and eventually dividing into a clone is called the cell cycle.
Exactly.
Now, when we think of cells, we often imagine them constantly bubbling and splitting apart in a frenzy of division, like in a time-lapse video.
Yeah, but that's not really how it works.
Right. Because when you actually look at the timeline of a cell's life, that division process is just a tiny fraction of its existence. Most of a somatic cell's life is spent in a phase called interphase.
Interphase.
During interphase, the cell is not dividing. It is just existing. It's hanging out in the tissue, doing whatever specialized job it was built to do, whether that's flexing a muscle or secreting a digestive enzyme.
Just doing its daily work.
And while it's doing that job, deep inside the locked vault of the nucleus, it is quietly, slowly synthesizing and copying its DNA, preparing for the future moment when it will eventually need to split.
Interphase is a period of relative safety for the DNA. The vault door is closed. The genetic material is somewhat shielded from external chemical chaos.
But it doesn't stay closed forever.
No. Eventually, the cell receives the biological signal that it's time to divide. It transitions out of the quiet growth of interphase and enters the chaotic, active phase of mitosis.
And here comes the danger zone.
Exactly. Mitosis is divided into four very distinct, highly choreographed substages: prophase, metaphase, anaphase, and telophase.
To understand why radiation is so deadly, we have to look at the mechanics of what happens to the vault during these four stages.
Let's walk through it.
It starts with prophase. During interphase, the DNA inside the nucleus is loosely packed. Imagine a massive tangled bowl of microscopic spaghetti.
A great way to visualize it.
But as prophase begins, that spaghetti starts to tighten up. It coils itself incredibly tightly into distinct, dense structures that we call chromosomes. And then the most critical event happens. The nuclear membrane, the thick wall of the vault that has been protecting the DNA, literally begins to dissolve and disappear.
It just melts away.
Yeah. At the same time, the cell starts building a temporary scaffolding called a spindle, stretching across the middle of the cellular space.
Vault is gone. The genetic material is now floating out in the open cytoplasm.
Which feels so vulnerable.
It is.
Yeah.
And this leads directly into the second stage, metaphase. The tightly coiled chromosomes migrate to the dead center of the cell.
Okay.
They line up in a perfectly neat single-file row along the equator of the cell, and they physically attach themselves to that spindle scaffolding we just mentioned. They are locked into position, waiting to be pulled apart.
I want to stop right here. I really want to put a massive flashing neon sign over the word metaphase.
It's that important.
Because when you dive into the radiobiology source material from McCowan, it makes a very specific, undeniable point about this exact moment in the cell cycle.
Yeah, it emphasizes it heavily.
It states that it is specifically during metaphase that scientists can actually evaluate and analyze a cell for radiation damage. Why metaphase? What is so special about this momentary lineup in the middle of the cell?
It completely comes down to visibility and vulnerability. Think about the physical state of the DNA during metaphase.
Okay.
As we just established, the protective nuclear vault is completely gone. The DNA has been dragged out into the open environment of the cell. It has been condensed into these thick, highly visible chromosomal packages, and it is strung up on a scaffolding in a neat little row.
Like lined up for inspection.
Precisely. From a diagnostic standpoint, if a scientist looks at a cell under a powerful microscope during the loose spaghetti phase of interphase, it is incredibly difficult to spot a single broken strand of DNA.
Right, because it's just a mess.
It's like trying to find a broken string in a massive ball of yarn.
Oh, that makes sense.
But during metaphase, the yarn is tightly wound into distinct spools and lined up on a shelf. If an X-ray photon passed through the body hours earlier, ionized an atom, and severed a bond in the DNA, The result of that microscopic atomic sabotage is suddenly laid bare.
You can actually see it.
Under the microscope, during metaphase, you will physically see the fragmented chunks of chromosomes. You will see pieces of DNA that have broken off and are just floating aimlessly in the fluid unattached to the spindle.
Wow.
You will see chromosomes that have inappropriately fused together into mutated, misshapen lumps. Metaphase is the exact moment the invisible atomic damage becomes undeniable, visible chromosomal devastation.
So the saboteur worked in the dark, but metaphase is when the sun comes up and you see the cracks in the foundation. It's the moment of exposure.
That's a poetic way to say it, but yes, exactly.
To finish the cycle, once they are lined up in metaphase, the cell moves to anaphase, where the spindle scaffolding violently retracts, literally ripping the chromosome pairs apart and dragging one complete set of DNA to the north pole of the cell and the other identical set to the south pole.
A physical separation.
And finally, in telophase, the cell physically pinches itself in the middle. The text refers to this as the dumbbell effect until it snaps into two.
Amen.
The nuclear vaults magically reappear around the two new sets of DNA, the chromosomes uncoil back into loose spaghetti, and you suddenly have two separate, identical cells entering interphase, ready to start the whole cycle over again.
In understanding that dynamic, chaotic process of division, the opening of the vault, the lining up of the naked DNA, the physical ripping apart of the chromosomes, it leads us directly to the most critical rules of engagement in the entire field of radiobiology.
Okay, so we know how cells divide. We know the mechanical steps. But the central question remains. When a wave of ionizing radiation washes over the body, are all of these trillions of cells equally vulnerable to the attack? It's the big question.
Right, like, does a cell in the brain react the exact same way as a cell in the stomach?
Based on what we just discussed about the vault being open during division, what does your intuition say?
My intuition says no. If the danger zone is when the DNA is exposed and dividing, then the cells that are dividing the most frequently must be the ones taking the most casualties, right? Is it an unequal battlefield?
You have just intuitively deduced the foundational bedrock of radiobiology.
I'll take it.
It is a wildly unequal battlefield. And this inequality is governed by a strict biological doctrine known as the law of Burgoni and Tribondeau.
Burgoni and Tribondeau, let's dig into that.
Yes. Named after two French scientists, Jean Burgonier and Louis Tribondeau, who formulated this principle all the way back in 1906, shortly after the discovery of X-rays.
Wow, so over 100 years ago.
They observed how different tissues reacted to radiation and realized there was a mathematical predictability to the destruction.
It wasn't just random damage. No, not at all. Their law dictates that a cell's sensitivity to radiation is entirely strictly dependent on two factors: the cell's state of maturation and its rate of metabolism.
Let's unpack the specific tenets of this law because it completely dictates how radiation sickness manifests in the human body. The source material outlines 4 specific rules of vulnerability under this law.
Let's hear them.
Rule number 1. Stem cells are vastly more sensitive to radiation than mature cells. And just to clarify, when we say stem cells here, we are talking about immature, undifferentiated precursor cells, cells that haven't quite decided what their final job in the body is going to be yet.
Correct. They are raw potential.
Okay, rule number 2. Young tissues and organs are inherently more sensitive to radiation than older, fully developed tissues and organs. Rule number 3. Cells with a high level of metabolic activity, meaning cells that are burning a lot of energy, consuming a lot of resources, and working frantically, are significantly more sensitive. And finally, rule number 4, which confirms what we just guessed. Rapidly dividing cells, cells that go through that mitosis cycle and open their nuclear vaults constantly, are always more sensitive than cells that rarely divide.
When you synthesize those 4 rules together, a very clear biological profile of a radiation victim emerges.
Right.
The busier a cell is, the faster it is rushing through the cell cycle. The more immature it is, the higher its metabolic furnace is burning. The easier it is to completely destroy with ionizing radiation.
That's an easier target.
Much easier. Conversely, a cell that is highly mature, highly specialized, has a low metabolism, and just sits quietly doing its singular job without ever bothering to divide and open its vault.
Yeah.
That cell is functionally armored against radiation.
I really want to visualize this because it's so critical. Let's go back to our city metaphor, but let's zoom in on the industrial district. Let's look at 2 different factories.
Okay, 2 factories.
In the first factory, you have a master craftsman, a highly mature, specialized worker. They are building a ridiculously complex, bespoke piece of machinery. A jet engine, let's say.
Sounds specialized.
Very. They work slowly, carefully, referencing their blueprint once a day, and it takes them an entire month to build one engine. They are not rushed.
Right.
If our invisible saboteur sneaks into that factory and throws a wrench onto the craftsman's workbench, what happens?
Not much, probably.
Exactly. The craftsman probably just sighs, brushes the wrench onto the floor, and goes back to carefully polishing a turbine blade. The disruption is minimal because the process is slow and stable. That craftsman is your mature, slow metabolism, non-dividing cell.
Okay, I like that. What about the second factory?
So go across the street to the second factory. This is a high-speed assembly line. It is churning out thousands of basic, unspecialized plastic parts every single minute. The conveyor belts are moving at lightning speed. The robotic arms are wildly swinging back and forth. The workers are frantic, constantly reaching for new raw materials.
Chaos.
Pure chaos. It is a state of high-energy, chaotic production. Now, if the saboteur walks into that factory and throws a wrench into the gears of the main conveyor belt,
Whole thing crashes.
the results are catastrophic. The belt snaps, the gears shatter, basic parts go flying everywhere, the robotic arms crash into each other, and the entire production line grinds to a violent, sparking halt in seconds.
Oh.
That frantic assembly line is your rapidly dividing, immature, highly metabolic stem cell. It relies entirely on perfectly timed rapid momentum. It simply cannot handle the atomic disruption of an ionized molecule.
That factory analogy perfectly encapsulates the physical reality of the law of Brogoni and Tribondeau. And the reason we spend so much time exploring this law is not just for academic curiosity.
No.
It is because this specific principle dictates the real-world applications, the medical dangers, and the life-saving therapies involving radiation.
Give me an example.
For instance, this law is the exact biological reason why radiation exposure is vastly, exponentially more dangerous to a developing fetus in the womb than it is to a full-grown adult.
Because a fetus is essentially entirely made up of the second factory.
Precisely. Think about fetal development. A fetus is not a tiny adult. It is a massive, incredibly dense cluster of undifferentiated, highly metabolic, rapidly dividing stem cells.
Which is constant construction.
It is rushing to build an entire human body from scratch in 9 months. The cell division is constant and frantic. The nuclear vaults are constantly open.
So it hits every single rule.
A developing fetus perfectly aligns with all 4 tenets of extreme vulnerability under Brogoni and Tribondeau. A dose of radiation that an adult mother might absorb with nothing more than minor, easily repaired cellular damage could cause catastrophic systemic developmental failure in the fetus.
Because the radiation acts like a wrench thrown into an assembly line that is operating at maximum capacity.
Exactly. It's devastating.
It's sobering to think about. But the flip side of that coin is just as profound, right? Because this exact same law of vulnerability is how we weaponize radiation to save lives.
Yes, is it?
It explains the entire foundation of radiation oncology.
Yes. How do we fight cancer? First, we have to define what cancer actually is. A cancer tumor is not a foreign invader like a virus. Cancer is your own cells, but they have broken their genetic programming. Cancer is, by definition, a mass of rapidly dividing, highly metabolic, immature, undifferentiated cells that are proliferating completely out of control.
They are an assembly line that has had all the safety limiters removed. They are just blindly churning out copies of themselves as fast as possible, consuming massive amounts of the body's energy to do it.
Exactly. And because they are behaving like that frantic assembly line, cancer cells perfectly fit the criteria for extreme radiosensitivity.
Oh, I see.
They are drastically more vulnerable to radiation than the healthy, mature tissue surrounding them.
So they're the easiest target in the room.
Yes. Therefore, an oncologist can target a tumor with a very specific dose of focused radiation. The dose is calibrated to be high enough to absolutely shatter the constantly open DNA vaults of the fast-dividing cancer cells, killing the tumor.
But the healthy cells.
Crucially, that same exact dose is low enough that the surrounding, mature, slow-dividing, healthy cells, the master craftsmen with their vaults closed, can endure the hit, utilize their enzymatic repair crews, and survive the treatment. The cure for cancer relies entirely on the law of Brogoni and Tribondeau.
The very nature of the disease, its chaotic, rapid growth, is the exact weakness that allows the treatment to work. It's a brilliant biological exploitation.
It really is.
Okay, so we have the theory. We understand the rules of engagement. Now let's make it tangible. Let's map this abstract law directly onto the physical geography of the human body.
The front lines.
Yeah, let's look at the front lines and see exactly what breaks down first when a body is exposed to a field of radiation.
The source material provides an excellent breakdown of this, categorizing the body's various cellular populations into high, intermediate, and low radiosensitivity.
Let's start with the highest.
Let's begin at the extreme end of the spectrum. The cells with the absolute highest sensitivity. These are the biological structures that will suffer severe damage or complete destruction from a relatively low dose of radiation, specifically in the range of 2 to 10 gray, which is roughly 200 to 1,000 rad.
Okay, 2 to 10 gray. The source highlights two specific types of cells that share the unfortunate title of being the most radiosensitive targets in the entire human anatomy.
What was the first one?
The first type are the spermatogonia. These are the immature reproductive stem cells located in the testes.
Which tracks perfectly.
It tracks perfectly with everything we've learned. They are genetic cells, their entire purpose is division, they are constantly active, and they are immature precursors. They hit every marker for extreme vulnerability.
Yep.
But the second most sensitive cell type in the body is arguably even more critical to day-to-day survival, the lymphocytes, the
Yeah.
white blood cells.
We really need to spend some time on the lymphocytes because understanding their vulnerability is the key to understanding why radiation is so lethal on a systemic level.
Okay, explain.
Lymphocytes are the elite frontline soldiers of the human immune system. Their job is to patrol the bloodstream and the lymphatic fluid, constantly searching for foreign antigens, bacteria, viruses, toxins.
Right.
When they find an invader, they sound the alarm and begin rapidly producing specific antibodies to neutralize the threat.
Sounds like a crucial job.
It is, but here is the critical detail. A mature lymphocyte has an incredibly short lifespan. It only lives for about 24 hours.
Wait, 24 hours, your entire immune system is replaced daily.
A vast majority of it, yes. The turnover rate is astronomical. Because they only live for a day, the bone marrow is acting as a massive high-speed factory, constantly churning out millions of new precursor lymphocytes every single hour just to maintain a baseline immune defense.
So it's the ultimate assembly line.
It is a state of perpetual high metabolism cellular division. Therefore, when a dose of radiation sweeps through the body, it is like a scythe cutting through a field of wheat. The radiation instantly shatters the dividing stem cells in the bone marrow, halting the production line.
The factory goes dark?
And because the lymphocytes currently circulating in the blood will naturally die of old age within 24 hours anyway, the body's white blood cell count plummets catastrophically almost overnight.
Because there's no replacements coming.
The immediate result is that the body loses its natural ability to combat infection. The immune system completely crashes.
Wow.
Suddenly, a minor cut, a common cold virus, or even the natural, normally harmless bacteria living in your own digestive tract becomes a lethal systemic threat.
That's terrifying.
The patient doesn't die directly from the radiation damaging an organ. They die from overwhelming opportunistic sepsis because the defensive army was wiped out and no reinforcements were printed.
That is a terrifying domino effect. The loss of a single 24-hour cell type leads to total biological surrender.
It's a house of cards.
Okay, moving down the anatomical map, we encounter the gastrointestinal system.
Ah, the GI tract.
The source is very explicit here. It states that the small intestine is the most radiosensitive portion of the entire GI tract, much more sensitive than the stomach or the large intestine. Why is the small intestine such a weak point?
To understand that vulnerability, we have to look closely at the microanatomy, the inner lining of the small intestine.
Okay.
The inside of your intestine is not a smooth, flat pipe. If it were, food would just slide through without being absorbed.
Right.
Instead, the lining is folded into millions of tiny, microscopic, finger-like projections called villi. These millions of fingers massively increase the internal surface area of the intestine.
To catch all the nutrients.
Exactly. As digested food passes over them, the cells on the surface of these villi absorb the water, the sugars, the proteins, and transfer them directly into the surrounding capillary blood vessels. They are the intake valves for the body's fuel.
But the environment inside the small intestine is incredibly hostile, right? I mean, you have highly acidic stomach churn, you have digestive enzymes designed to break down tissue, and you have the physical friction of food constantly scraping against these delicate little fingers.
Exactly. The villi are under constant physical and chemical assault. The mature, absorbing cells at the very tip of the fingers are constantly being worn down, dying, and sloughing off into the digestive tract.
So they have to be replaced.
Constantly. To survive this continuous wear and tear, the intestine has to constantly regenerate its lining. So at the base of every single one of these finger-like villi, down in the microscopic valleys of the intestinal lining, there's a tiny pit.
Okay.
And inside that pit is a cluster of what we call crypt cells.
The crypt cells. It sounds ominous, and in the context of radiation, it absolutely is.
The crypt cells are the dedicated stem cell factories for the intestinal lining. They are rapidly dividing, highly metabolic, undifferentiated cell populations. Their entire job is to constantly undergo mitosis, creating new cells that slowly migrate up the sides of the villi to replace the mature cells that are dying at the top.
It's a continuous upward conveyor belt of cellular renewal,
Yes.
which means, according to the law of Bragoni and Tribando, those crypt cells have a giant glowing bullseye painted on them.
They absolutely do. So visualize what happens when a high dose of penetrating radiation hits the abdomen. The mature non-dividing cells at the very tips of the villi, the craftsmen, they might actually survive the initial blast. They keep absorbing nutrients for a little while.
But down in the valleys,
Down in the valleys, the radiation absolutely massacres the rapidly dividing crypt cells. The DNA vaults are shattered. The factory at the bottom of the conveyor belt is completely destroyed.
when the supply line is cut.
Yes. The cells at the top of the villi continue to wear down and die from the digestive acids, as they always do. But now, there are no new cells migrating up from the crypts to replace them.
Oh, man.
Within days, the villi begin to shrink. The finger-like projections shorten. They flatten out. The smooth lining of the intestine becomes bare.
And what happens when it's bare?
The textbook describes a horrific, inevitable progression. Without its protective cellular layer, the bare intestinal wall begins to ulcerate. It develops open sores. It hemorrhages, bleeding freely into the gut.
Oh, wow.
And eventually, it attempts to heal by scarring over, a process called fibrosis, which inevitably leads to tissue necrosis or death.
And the functional result for the human being experiencing this.
Because the villi are completely gone, the physical mechanism for absorbing fuel is destroyed. The patient can drink gallons of water and eat thousands of calories, but the intestine simply cannot absorb it into the bloodstream.
So they're starving.
The body is essentially starving and dehydrating to death from the inside out, while simultaneously losing massive amounts of fluids and blood through the ulcerated lining. And, to make matters worse, exposing the bloodstream to the bacteria normally kept safely inside the gut.
It's a staggering, cascading failure. It starts with an ionized atom inside a microscopic crypt cell, and it ends with the total collapse of the body's energy intake system.
That's the reality of it.
Okay, let's move from the inside of the body to the outside. Let's
Yeah.
look at the skin and the hair, because this is often the most visible marker of radiation exposure in popular culture.
Right, the classic signs.
The skin is a perfect, highly visible microcosm of our vulnerability rules. The skin isn't just one layer, it's a stratified organ. The outermost layer, the epidermis, the skin you can touch right now, consists mostly of mature, heavily specialized, non-dividing cells.
Yeah, dead cells mostly.
Right, the very top layer is just dead cells acting as physical armor. Because they are mature and non-dividing, this outer layer is fairly resistant to radiation. However, right beneath them, acting as the foundation of the epidermis, is a layer called the basal cells.
And the basal cells are the stem cells of the skin. They're constantly dividing, pushing new skin cells upward to replace the ones you shed every day.
Correct. So, when a field of radiation hits the skin, it largely ignores the dead armor on top, but it deeply damages those rapidly dividing basal cells underneath.
What's the immediate effect?
The immediate acute changes following a high localized dose include severe inflammation and a condition called erythema, which presents as a deep, severe, sunburn-like redness as the blood vessels react to the cellular distress.
Like a really bad sunburn.
Yeah, but as the days pass, a much more severe condition occurs: desquamation.
Asquamation.
The text defines this as denudation. Let's explain what that physically looks like, because it is essentially a failure of cellular gravity.
Okay, explain that.
The basal cells aren't just factories. They are the anchors holding the top layers of skin to the underlying tissue. When the radiation kills off the basal layer, the mature skin on top suddenly loses its anchor. It has nothing holding it down.
Oh, that sounds awful.
So desquamation is the actual physical peeling, blistering, and sloughing away of entire sheets of skin, leaving raw, weeping tissue underneath.
It's gruesome, but it perfectly illustrates the loss of those dividing cells. And we see a nearly identical biological mechanism with hair follicles.
So, right, hair loss.
Hair is constantly, steadily growing, which means the cells at the root of the follicle are in a state of rapid, continuous division. They are highly metabolic stem cells.
Targets.
If the body receives a moderate dose of radiation, it disrupts that division, leading to temporary epilation or alopecia, the medical term for hair loss. The follicle stops producing hair until it can repair its DNA.
This is why cancer patients lose their hair.
Exactly. Patients undergoing radiation therapy or systemic chemotherapy, which also targets dividing cells, frequently lose their hair. The treatment is intentionally hunting rapid cellular division, and the hair follicles are caught in the crossfire.
But it grows back, usually.
Usually. But if the localized radiation dose is high enough, it won't just pause the follicle, it will permanently destroy the stem cells, resulting in permanent, irreversible baldness in that specific area.
Okay, so we've mapped out the highly vulnerable casualties, the reproductive factories, the immune system's front line, the digestive intake valves, and the skin's anchors.
We covered the weak points.
Let's flip the script. In this war zone of ionizing energy, what are the bulletproof cells? What cells in the human body can take a direct hit from a wave of radiation and essentially just shrug it off?
The cells with the absolute lowest radiosensitivity, the most durable biological structures in the human body, are muscle cells and nerve cells.
Brain cells and biceps, why are they the tanks of the biological city?
Because they represent the absolute polar opposite of the stem cells we've been agonizing over. By the time you reach adulthood, your muscle fibers and your nerve cells, your neurons, are incredibly mature.
Okay.
They are highly intricately specialized to perform complex functions, like transmitting electrical impulses or contracting to lift a heavy weight.
So they're the master craftsmen.
Exactly. But the most vital factor is their division rate. Adult muscle and nerve cells rarely, if ever, undergo mitosis. They do not divide. The neurons you have in your brain right now are largely the exact same neurons you've had for years.
Their nuclear vaults are permanently locked shut.
Yes. Because the vault is closed and the DNA is tightly packed away in interphase, the genetic blueprint is heavily shielded from atomic disruption. It takes a massive, overwhelming dose of radiation specifically, a localized dose in excess of 50 gray or 5,000 RAD, to cause significant deterministic damage to pure nerve tissue.
That's a huge dose.
It is. They are the ultimate craftsmen of the cellular factory, completely unfazed by the saboteur's attempts to disrupt an assembly line that simply doesn't exist.
Okay, so we have firmly established what parts of the body get damaged based on how fast they divide. Now, we need to shift our focus to the timeline.
The timeline is crucial.
Right, we need to look at how that damage manifests over time, because radiation is not a simple poison that acts the exact same way every time.
Not at all.
The source material divides the human biological response to radiation into two very distinct categories, representing two completely different timelines of toxicity: deterministic effects and stochastic effects.
Understanding the difference between these two effects is arguably the most practical knowledge anyone can take away from this discussion, because it dictates how we manage risk in medicine and industry.
Let's begin with deterministic effects.
Mm-hmm.
Think of this as the immediate, brute force impact of radiation. The formal definition of a deterministic effect is a biologic response, where the severity of the response varies directly with the radiation dose.
The severity varies.
Meaning, if you get a little bit of radiation, you get a mild reaction. If you get a massive blast of radiation, you get a devastating reaction.
Precisely. It is a linear relationship of destruction. And a key defining characteristic of deterministic effects is that there is almost always a measurable dose threshold.
A threshold.
Yes, there is a minimum amount of radiation energy required to trigger the effect at all. If the dose you receive is below that specific threshold, nothing happens. The repair mechanisms handle the minor damage, and you show absolutely no symptoms.
But if you cross it,
the moment you cross above that threshold, the effect occurs, and the higher you push the dose past the threshold, the more severe the resulting injury.
these are the fast, aggressive responses. The text notes that deterministic effects are typically produced by relatively high doses of radiation delivered over a very short period of time in acute exposure, and you don't wait years to see the results. The damage is observed within days or weeks.
The examples are stark and immediate. The erythema, or skin burn we discussed earlier, is a classic deterministic effect. If you place your hand in a high-intensity radiation beam for 1 second, you are below the threshold. Nothing happens.
Yeah.
If you leave it there for 10 seconds, you cross the threshold and develop a mild red sunburn. If you leave it there for a minute, the severity scales up and you experience severe blistering and tissue death, massive organ dysfunction, acute cell death, drops in white blood cell counts.
Mm-hmm.
These are all deterministic.
Okay, that makes logical sense. It acts like heat. A little heat warms you up, a lot of heat burns your skin off.
Exactly.
But now I have to contrast that with the second category, stochastic effects. And this is where radiation becomes deeply unsettling. This is the long-term gamble.
The gamble.
Yeah. In a stochastic effect, it is not the severity of the response that increases with the dose. It is the incidence or the probability of the response occurring at all.
I often explain stochastic effects as a microscopic, terrifying lottery.
Let's expand on that lottery analogy because it is the perfect way to understand this.
Go for it.
If you buy one lottery ticket, your odds of winning the jackpot are incredibly low, almost zero, but not quite zero.
Right.
If you buy 10,000 lottery tickets, your odds of winning go up significantly. You have a much higher probability of holding the winning number.
Mm-hmm.
But, and this is the crucial part, if you do win, the size of the jackpot doesn't change based on how many tickets you bought. The prize is exactly the same whether you bought one ticket or 10,000.
That is the exact mathematical reality of a stochastic radiation effect. A stochastic response is typically produced by low doses of radiation accumulated slowly over a very long period of time. And the effects aren't seen in days.
They incubate.
They are hidden. They're observed over months, years, or even decades.
This is the saboteur who removes a single piece of mortar from a hidden pipe, sneaks out of the city, and 20 years later the pipe bursts under pressure and floods a neighborhood.
That's it, exactly. And the text highlights a vital point. Stochastic effects are the primary overriding concern for diagnostic imaging.
Oh, really?
Yes. When you go into a clinic for a routine CT scan or a chest X-ray, the technicians are not worried about deterministic effects. The dose is so incredibly low that you are nowhere near the threshold for a skin burn. They aren't worried about immediate cell death.
Okay.
What they are tracking, what they are trying to minimize with their lead aprons and calibrated machines, is your stochastic risk.
Because the jackpots in this biological lottery are severe life-altering conditions.
Exactly. Stochastic effects include long-term genetic damage, overall lifespan shortening, and most prominently and dangerously malignant diseases, specifically cancer.
Right.
The source material provides a stark historical example. Epidemiologists tracking large populations have predicted a measurable rise in the incidence of leukemia over a 20-year period, directly correlated to the steadily increasing amount of man-made diagnostic radiation exposure to the general public.
Wow, 20 years later.
And cancer perfectly follows the lottery rule. It is binary. You either have leukemia or you don't. Receiving a slightly higher dose of diagnostic radiation 20 years ago doesn't give you a worse version of leukemia today. It simply increased your mathematical odds of a mutated cell surviving the repair process and developing into the disease in the first place.
Other cancers, too?
Oh, absolutely. Other major cancers, bone cancer, lung cancer, thyroid cancer, breast cancer, they all follow this exact same stochastic, probabilistic model.
And to help medical professionals visualize this difference, the source briefly covers dose-response curves. These are the mathematical graphs that scientists use to plot how the human body reacts to different levels of exposure.
Right.
You have the x-axis mapping the dose of radiation and the y-axis mapping the biological response. You can have linear curves where the response is directly, predictably proportional to the dose. It's just a straight diagonal line pointing up and to the right.
And nonlinear curves.
Right, where the response might curve up slowly at first and then suddenly spike upward at higher doses.
But the truly important distinction on those graphs, the line that separates a burn from a cancer risk, is the starting point on the graph. The distinction between a threshold curve and a non-threshold curve.
Okay, break that down.
Deterministic effects, the skin burns, the organ failure sit firmly on a threshold curve. If you trace the line on the graph backward, it doesn't intersect at 0 on the dose axis. It starts further down the x-axis.
Because there's a safety zone.
Exactly. This visually proves that a minimum defined dose is required before you see any response whatsoever. The area before the line starts is the safety zone.
But stochastic effects, the long-term cancers, the genetic mutations, they sit on a non-threshold curve.
Yes.
If you trace a non-threshold line backward, it intersects at absolute 0, right at the origin corner of the graph.
And the implication of that 0 starting point is profound.
Yeah.
It means that any dose of radiation, no matter how microscopically small, even a single scattered photon from a dental X-ray has the potential to produce a biological response.
Even one photon.
It might be a 1 in a trillion chance that the photon hits the exact wrong strand of DNA and the repair enzyme makes the exact wrong mistake, leading to a tumor a decade later. But the mathematical chance is not 0. There is no absolute safety zone.
Which brings us firmly and unavoidably back to the very beginning of our deep dive. This non-threshold reality is the exact reason the L-Kaori principle exists.
You got it.
Because stochastic effects mean that any exposure could hypothetically be the winning lottery ticket for a mutation, we must relentlessly keep all exposure as low as reasonably achievable. We only accept the risk when the medical benefit is undeniable.
Absolutely.
Okay. We have established the subatomic theory, we have explored the mechanics of cell division, we have mapped the vulnerabilities of the tissues, and we have plotted the long-term timelines of toxicity.
We've covered a lot of ground.
We have. Now we have to look at the absolute worst-case scenario. Up until now, we've mostly been discussing localized damage, a beam of radiation hitting the skin, or a targeted dose hitting a tumor, or the statistical risk of a low-dose X-ray.
Right.
But what happens when the entire biological city is attacked simultaneously? What happens when the whole body is exposed to a high-penetrating dose of radiation all at once?
When that happens, the deterministic effects, the immediate brute force destruction of cells are no longer localized. They cascade violently across multiple organ systems, leading to total systemic failure.
The worst-case scenario.
The medical term for this catastrophic event is acute radiation syndrome, commonly abbreviated as ARS. It is also known colloquially as radiation toxicity or radiation sickness.
The source material provides a very specific definition for this condition. ARS is an acute illness caused by the irradiation of the entire body, or at least a significant majority of it, by a high dose of penetrating radiation, delivered in a very short period of time, usually a matter of minutes.
Minutes, yeah.
The textbook threshold for this systemic nightmare to begin is an acute whole-body dose of 1 gray, or 100 RAD. To put that in perspective, that is thousands of times more radiation than a standard medical X-ray, delivered all at once.
And the progression of acute radiation syndrome is not chaotic. It follows a very rigid, highly predictable, and frankly cruel timeline, consisting of 3 distinct sequential stages.
3 stages. What's the first one?
The first stage is the prodromal stage. This is the body's immediate initial alarm bell.
It's the city's early warning sirens going off.
Yes. Usually occurring within hours of the massive exposure, the prodromal stage is characterized by acute nausea, vomiting, and diarrhea.
The body knows something is wrong.
Even before the massive cellular die-off fully registers, the body fundamentally recognizes that a massive toxic insult has occurred at the chemical level, and the gastrointestinal system reacts violently in an attempt to purge whatever poison it thinks it just ingested.
It's a classic biological rejection response. But it doesn't last, does it? The nausea eventually fades, and the patient transitions into the second stage, the latent stage.
The latent state.
The text notes that the latent stage can last anywhere from a few hours to several weeks, entirely depending on the severity of the initial dose. During this stage, the patient suddenly feels better, the vomiting stops, there's a returning sense of well-being.
It's a cruel trick.
They might even be walking around, talking, eating. To an untrained observer, they might mistakenly be thought to be recovering from whatever brief illness they had. But this stage is a terrifying illusion.
An illusion.
I want to use an analogy to explain what is physically happening inside the body during the latent stage. Imagine you are driving down the highway at 70 miles an hour in a luxury car. The air conditioning is blowing cold, your favorite music is playing on the radio, the ride is perfectly smooth, everything feels fine.
Okay.
But what you don't realize is that 5 miles back, your engine completely exploded and died.
That is a chillingly accurate comparison.
You are still moving at 70 miles an hour because you have physical momentum. The battery is still running the radio and the AC, the tires are still rolling. To the passengers inside the cabin, nothing has changed. The environment is stable.
But the reality is,
But if you press the accelerator pedal, nothing happens. The engine is a smoking crater. No more power is being generated. You are just coasting. You are simply running out the clock on your forward momentum until friction eventually drags the car to a dead halt.
and applying that mechanical momentum to the biology of the latent stage explains exactly why the patient feels healthy.
How so?
Remember our discussion about the mature cells versus the stem cells. The mature red blood cells currently circulating in the patient's veins are highly resistant to radiation. They survived the blast.
Oh.
They are still actively carrying oxygen to the brain and the muscles. The mature cells lining the top of the intestinal villi are still absorbing whatever nutrients they can. The body's momentum is still carrying it forward. The patient feels fine because the cells currently doing the work are still alive.
But underneath the surface.
Down in the bone marrow and the intestinal crypts, the engine is dead. The rapidly dividing stem cells have been completely, utterly wiped out by the radiation blasts.
The factories have been leveled.
Exactly. And blood cells naturally die of old age every few days or weeks, so the patient is coasting. They feel fine today, but the mature cells are slowly aging and dying out, and there are absolutely zero reinforcements being manufactured to replace them. The clock is ticking down strictly based on the natural lifespan of the surviving mature cells.
And when that biological momentum finally runs out, when the car rolls to a halt on the highway, the eye of the needle closes, the illusion shatters, and the patient plunges into the third and final stage, manifest illness.
Manifest illness.
This is the horrific, violent return of symptoms. And the exact nature of the manifest illness, what specific organs fail, and what ultimately causes the death of the patient depends entirely on the exact dose of radiation received, because the dose dictates which cellular system reaches its breaking point first.
The source outlines 3 specific, distinct syndromes of manifest illness, categorized by the dose threshold required to trigger them. Let's walk through these thresholds of systemic failure.
Okay, what's the first syndrome?
The first is hematopoietic syndrome, which is more commonly known as bone marrow syndrome. The syndrome occurs when the acute whole-body dose is between 1 and 10 gray.
Which is the lowest threshold for lethal ARS. Why does the bone marrow fail first?
If you recall our map of cellular vulnerability, the bone marrow is the manufacturing center for the blood, including the red blood cells, the platelets, and most critically, those highly sensitive, rapidly dividing lymphocytes we discussed earlier.
The 24-hour lifespan ones.
Exactly. At a dose between 1 and 10 gray, the radiation is strong enough to completely eradicate the stem cells in the marrow, but not necessarily high enough to instantly obliterate the digestive tract or the brain.
So what happens?
So, during the manifest illness phase of hematopoietic syndrome, as the latent period ends and the circulating blood cells die off without replacement, the patient suffers severe, cascading hematological failure. They develop profound anemia as the oxygen-carrying red blood cells deplete, leading to extreme lethargy and organ hypoxia. They lose their platelets, leading to uncontrolled internal hemorrhage.
But the fatal blow is the immune system, right?
Yes. The fatal blow is usually leukopenia, the catastrophic drop in white blood cells. The immune system ceases to exist. Death typically occurs within 10 to 60 days of the initial exposure, primarily because the body becomes a defenseless breeding ground for massive, overwhelming, opportunistic infections. A simple ambient bacteria in the lung becomes a lethal pneumonia.
Wow. But if the dose is pushed even higher, the timeline accelerates dramatically, right?
Very much so.
If the whole body dose falls between 10 and 50 gray, the patient bypasses the long decline of bone marrow failure and immediately enters gastrointestinal syndrome.
Right into the GI failure.
At this dose level, the bone marrow is absolutely destroyed, of course. But the patient won't live long enough to die from an infection in 60 days because the GI tract collapses long before the blood supply completely depletes. Death in gastrointestinal syndrome occurs brutally fast, usually in just 4 to 10 days.
And this takes us directly back to the crypt cells in the microscopic valleys of the small intestine. We mentioned that they are highly sensitive, but they are deeply embedded in tissue and require a slightly higher dose of raw energy to completely sterilize than the diffuse liquid marrow in the bones.
But at 10 to 50 gray, it's sterilized.
That threshold is violently crossed. The entire cellular lining of the GI tract is sterilized. The crypt stem cells die instantly. Over the brief latent period, the villi slough off, leaving the intestinal walls completely bare.
Which leads to
The symptoms of manifest illness here are profound and horrifying. The patient goes into systemic shock. They suffer from extreme lethargy, anorexia, and severe bloody diarrhea as the digestive tract hemorrhages. The critical barrier separating the trillions of bacteria in the gut from the circulating bloodstream is gone, allowing massive internal sepsis.
And they can't absorb food or water anyway.
Furthermore, the body fundamentally loses the physical ability to absorb water or nutrients. The rapid dehydration, electrolyte imbalance, and systemic shock lead to a swift death.
And then we reach the final, most extreme threshold of acute radiation syndrome, CNS, or central nervous system syndrome.
The highest dose threshold.
This occurs at unimaginable, catastrophic whole-body doses greater than 50 gray. At this level of exposure, the concept of a latent period almost vanishes. Death is almost immediate, typically occurring in 0 to 3 days.
That's incredibly fast.
But wait, I have to stop here because this seems like a massive biological contradiction. Earlier, we stated definitively that mature nerve cells and brain cells are the ultimate bulletproof cells. They don't divide. They are the most radiation-resistant cells in the entire human body, capable of withstanding massive doses without deterministic damage.
That's true.
So if the neurons are essentially immune to radiation, why does a massive dose instantly kill the central nervous system?
It is a brilliant observation, and it highlights the ultimate vulnerability of complex biological systems. You
Yeah.
are entirely correct. If you extracted a single mature neuron, place it in a petri dish, and hit it with 50 gray of radiation, the neuron itself might survive the initial ionization. Its vault is closed, its DNA is protected.
Right.
But inside the human skull, the brain does not exist in a vacuum. A neuron cannot survive on its own. It relies on a vast, intricate, microscopic infrastructure to survive. Specifically, it relies on a massive network of tiny blood vessels and capillaries to constantly supply it with oxygen, carry away toxic byproducts, and maintain the delicate fluid pressure of the brain cavity.
Ah, the blood vessels.
And while the mature neurons are highly resistant to radiation, the cells lining those tiny blood vessels, the endothelial cells, are not. They possess an intermediate radiosensitivity.
Oh, man.
At acute doses exceeding 50 gray, the sheer brute force of the energy simply obliterates the microscopic vasculature of the brain. The capillaries physically break down and rupture.
The plumbing fails.
Completely.
Yeah.
Massive amounts of fluid and blood leak out of the ruptured vessels directly into the enclosed space of the brain cavity.
So the brain swells.
These symptoms are acute and violently neurological. Extreme confusion, profound nervousness, loss of coordination, convulsions, seizures, and severe meningitis, which is the elevated fluid pressure crushing the brain tissue.
So the nerve cells don't die from radiation damage to their DNA at all.
No, they don't. They die because the physical infrastructure supporting them instantaneously collapses. They are starved of oxygen and physically crushed to death under the rising pressure of their own leaking fluids.
The saboteur couldn't knock down the heavily armored power plant, so they just blew up the water mains and the roads around it, and the power plant drowned.
Exactly.
It's a sobering realization of how interconnected every single system in the biological city truly is.
It really is.
So what does this all mean? Let's take a breath and synthesize this incredible microscopic journey we've been on today. We started by looking at the smallest possible event in the physical universe. A single, invisible photon of energy colliding with an atom, knocking a solitary electron out of its orbit along a strand of DNA.
The ionization event.
We explored the rigid physics of how that tiny atomic absence ripples upward, altering chemical bonds and warping biological molecules. We saw how the body mounts a desperate defense, deploying enzymatic maintenance crews to restitch the broken blueprints.
But we also learned the mathematical reality of probability.
Right, the LRA principle demands we never take those repairs for granted.
We then stepped onto the cellular battlefield, discovering that the ultimate target of this invisible sabotage is the DNA vault, specifically when it's thrown wide open and exposed during the chaotic process of cell division, laying bare the chromosomes during metaphase.
And through the elegance of the law of Bergoni and Tribondeau, we learned the central, undeniable rule of radiobiology.
The fast-dividing cells.
Yes. Immature, rapidly dividing, highly metabolic stem cells are the most glaring vulnerabilities in the body, while mature, slow-moving, non-dividing cells act as biological armor.
And we tracked that exact vulnerability across the map of the human anatomy. We saw how the fast-dying lymphocytes cause the immune system to crash, how the destruction of the delicate crypt cells starves the intestines, and how the loss of basal anchors causes the skin to literally fall away.
And finally, we looked at the devastating, cascading collapse of acute radiation syndrome, tracking the cruel progression from the initial alarm of the prodromal stage, through the terrifying coasting illusion of the latent stage, right into the specific thresholds of manifest illness, where the bone marrow, the gut, and finally the brain's infrastructure succumb to the overwhelming energy.
So why should you, the listener, care about the intricacies of crypt cells and the physics of ionization? Why spend an hour diving deep into the microanatomy of the small intestine and the probabilistic math of stochastic effects?
Yeah, why does it matter?
Because you exist in a fundamentally radioactive universe. It is inescapable. Whether you are stepping into a doctor's office weighing the necessity of a routine diagnostic CT scan, whether you are reading complex geopolitical news articles about nuclear energy policy and reactor safety, or whether you are just taking a commercial flight across the country and being exposed to elevated cosmic background radiation, this science applies directly to your body and your life.
It really does.
Understanding the ALRO principle, Understanding the profound difference between a deterministic skin burn that requires a massive threshold and a stochastic cancer risk that operates like a microscopic lottery, and understanding the law of Bergoni and Trébandot. It empowers you.
It gives you the tools.
It allows you to separate Hollywood science fiction from cold biological fact. It gives you the intellectual tools to understand real, quantified risks versus perceived emotional risks when it comes to medical imaging, environmental exposure, and the amazing therapies we use to combat disease. It takes an invisible, terrifying threat and makes it comprehensible.
It shines a light on the saboteur. But as we wrap up this deep dive, I want to leave you with a final, somewhat provocative thought to mull over. It's a paradox that slowly emerged from everything we've read in the source material today.
What's the paradox?
Think about the stem cells. Think about the crypt cells in the microscopic valleys of your gut, the basal cells anchoring your skin, the hematopoietic cells frantically churning out immune defenders in your marrow.
The most vulnerable cells.
Exactly. The rapid, chaotic, endless division of these cells is the very mechanism that keeps you alive.
Yeah.
It is what allows you to heal a scrape on your knee, to fight off a winter cold, to constantly digest the food that fuels you. It is the ability to literally regenerate your own tissues day after day, month after month.
It's life itself.
It is the biological engine of your youth, your resilience, and your vitality. And yet, that exact same rapid division, that exact same biological engine of life, is the precise fundamental reason you are so profoundly, mortally vulnerable to the invisible sabotage of ionizing radiation.
That is quite the paradox.
The things that make your biological city so resilient and adaptable, the constant construction, the endless flow of new materials, the busy, high-speed factories are exactly what the atomic saboteur exploits to bring the city down. Our greatest evolutionary mechanism for survival is simultaneously our biggest biological Achilles heel.